But today we're going to talk about how do we talk about coordinate frames. So the idea is I've got my robot here, and I've got my coordinate frame. Oman's got all of them on his desk, and he's helpfully labeled. And what I can do is I could take my stapler. I forgot my tape roll, but we could think about stapling this coordinate frame onto this robot, and we could take another coordinate frame and we could staple it to something that's our reference, our point of reference. And then we can talk about what is a change in coordinates that's needed to describe where this coordinate frame, which I've bolted on to a specific part of my robot, and there's no limit to this. I could bolt one onto the arm, and if I had more hands, I could bolt one onto its feet. And I can talk about, what is the relationship between these coordinate frames, maybe from this one to the arm as it moves, or maybe from the base to the arm, because I want to know where is that arm so that I can figure out, the chainsaw that's attached to this arm, is it cutting the zombie or is it cutting the tree in Oman's backyard? Right? And so we need a little bit of rigor in order to represent these. So today we're going to jump into this coordinate transformations. How do I transform from one coordinate frame to another? And how we're going to do that is we're first going to talk just about the rotation aspect. So we're going to assume, remember, a rotation is just like a vector. A vector just tells you a direction of movement, and so we can move that vector around anywhere that we want, but it's always pointing at the same orientation. And so what a coordinate frame is, it's three vectors that are bound together so they're mutually orthogonal, and we use a right-handed coordinate frame. So these are right-handed coordinate frames. We're going to pass these around. So some of you believe in learning styles. So if you believe in tactile learning styles, you can touch this and you can learn better. We're going to take these, and these are just three vectors that are bound together. And so we can take those vectors, it's a free vector, and you can move them around. As long as they're always pointing the same way, we say that this is this rotation frame, and we can talk about how is it related to a base rotation frame. So as long as they have the same rotation everywhere, this rotation frame is telling you how you would rotate an object to get it in the same orientation as this one. And so today we're going to talk about three different definitions of rotation frames. If you didn't get one of these handy dandy papers, I got a whole stack of them right here. These are just handy for you to write down ideas, and then the worksheet is on the back. So we had a massive flood here, and so we're trying to record this lecture for those people who can't make it. But how that's going to impact that class is we have to remove some content. And so since this course builds on each other, it makes more sense to remove some content that's towards the end. And so we're going to sacrifice a little bit out of chapter 5. We're going to lose 2 lectures there, and we're going to lose an entire homework. Some of you are like, I'll post that homework online. You can do it for fun. You need to buy a robot arm bin. Welcome to the class. What we do with these worksheets is we use them to write a few notes. It's just for, the first page is just for your own good. For the back page, I say take a picture of it and submit it online. It'll be due before the next class. It's submitted through Blackboard. And as soon as you get your Blackboard ready, it'll be going. Okay, but this is how it's going to affect us. We're going to lose those. We're not going to change the date of the first exam, because the whole structure of this course is made so that the first exam forces you to review all this coordinate frames and how robots work. And then we have a little bit of a break, and then we ask you to do it again for the final exam. And that is done on purpose because we want this spaced repetition so that you can learn these things. So when you guys leave this class, you will have retained as much as possible. So that's why I did not change the order. It does mean that in exam 1, I'm not going to be able to ask you much about image plane geometry. Some of you already started to learn about image plane geometry because the last time we had class, it was right after an eclipse. And so we will talk more about that at that point. Something that's upcoming, there's always some training in different software. And so I like the training they offer at the CADs, and unfortunately I have no idea what they're doing with their schedule now that they changed this. That's the website. They have MATLAB training, they have Linux training, and it's all free. You just show up and they'll go through it. They teach you how to do parallel processing if that's part of your game. It's a nice resource that's provided. They've got all the computers with the software loaded. And, it's free. And so it's a nice opportunity, especially if you're just starting a graduate career. It's fun to see some of the technologies that are available to you. Right. With all that, I've got a couple handouts here that you'll want to grab. With all that, it's time to do a little bit of review. Where were we talking about last time? So when we talk about a coordinate frame, in order to specify a coordinate frame, I want to fully pin down where is this coordinate frame in space. I have to know a few things. The first thing I need to know is what is the location of the origin here. It takes how many numbers to do that?
3.
2. Oh no, more than 2.
3.
4. No, I want the origin of this. Where's the
3.
origin? Yeah, the origin is a point in 3 space. So it's just 3 numbers. So I need to know, what is this x, y, z displacement of this origin with regard to some base frame. I guess my base frame is moving. This is going to be my base frame, and this is why I should have brought tape today, so I could tape it down somewhere. We're going to pretend that's strapped down right there. We're not going to move it. If I move it, you say, hey. Right, we need to know the XYZ displacement of this point, and then we also need to know, what is the orientation of these vectors? And in order to fully specify the orientation of these vectors, we need 3 numbers. And there's lots of ways to come up with those 3 numbers. And so, for mathematical expediency, instead of talking about those 3 numbers, we're going to use those 3 numbers to generate a rotation matrix, which is a 3 by 3 matrix that has 6 constraints to it. So it really only has, the rotation matrix only has 3 degrees of freedom, but it's arranged in this 3 by 3 grid. And we do that for mathematical expediency, because once we have that rotation matrix, then to take any point and find out what happens when I rotate it, I just multiply it by that rotation matrix. So that's what we're doing here. But these rotation matrices is just telling you, so here you can see it's labeled X. Oh, it's got me erased already. It says X on here for the white one. And so this rotation matrix, the first column is saying, what is X1? This is X1 in my base frame. So if you look right now, X1 is a little bit in the X, a little bit in the Y, and a lot in the negative Z direction. Right? And then I say, second column is where is this Y in the base frame? If you look at it, you see it's a little in the negative X, a lot in the positive Y, and maybe a tad in the negative Z. And then the third column is what is this Z vector in the base frame? And so that's that's the mystery that's behind these rotation matrices. They're telling you where are each of these coordinate vectors, these base vectors, in that base frame. Right? And then we talked about a point P. Let's say, I'm going to write on your, it's erasable. So I'm going to label this point P. If I want to know where point P is, it's not enough. You have to say point P with respect to something. So how we do that is we do that with a superscript. The superscript tells us with respect to what are we talking. The subscript will add if we, if there's some confusion about which thing we're talking about. And so so point P, if I want to know it in coordinate frame 1, I'd be P superscript 1. And that would tell us, what's my coordinate frame in regard to this? And you say it's mostly Z, a little bit of negative Y. Whereas over here, there's no, if I say point P superscript 0, it's almost all in the X direction, a little bit in the Z. And so these are points. And I just move my point P. So with that, I want some audience participation. And so I want you to fish in your pockets for a pen. And your mom probably taught you not to do this. But label your thumb Z. Right? Label your index finger X. X. And some of you who are not left-handed, the majority of us, this is going to be very difficult. And then your middle finger Y. And I actually want most of you to do this. Some of you have taboos against writing on your hands, and you don't have to do that. But if you don't, well, you write on there. And if you really love this class, you can get little tattoos. But this is the right-handed coordinate frame. The rule is that x always, x cross y gives you z. And so if I cross x and bring x to y, I get my z. The right-handed coordinate frame, it corresponds with the right-handed screw. So if any of you had to take off cabinet doors during this hurricane, a lot of screwing going on there. And you actually had to go on the negative Z because we wanted to pull that screw out of the cupboard. And so you were spinning it this way. But if you wanted to put it in, you'd spin in the positive Z-axis. All right, so now we need to do a little bit of review. And these are our basic coordinate frame, our basic rotation matrices. So the first one that we have is I want to rotate, and this subscript is what we're going to be using a lot in this class. So the first one is I want to take my rotation matrix and I want to rotate it around my current x-axis by some degree theta. So I'm rotating around the x-axis by theta. And we have to write this one, and I want you to write it down because these things are stuff we'll be using quite a bit. You already have it memorized, and beat me to it. But I've given you these little hints that if you're rotating around an axis, then you're not going to change that coordinate frame. So you see x is always pointed in the same direction. So we get 1 for free. Remember, this is x, 1 and 0, y 1 and 0, z 1 and 0. You got 1, 0, 0. And then we've got a bunch of basic properties of rotation matrices. The first is that all the columns are unit length. And all the rows are unit length. And so we take the norm of these, which means that this row also has to be zeros. And so, that simplifies some of our life down. And then what we're doing is we're rotating these other axes around here. And so this is where, some of you have nice mnemonics to remember it. But I want to show you a shorthand that we're going to be doing in this class. When I say cos of theta, that's like 5, 6 characters to write. That's crazy. We're not going to do that. We're going to go C underscore theta. Like, wow, that's like a third the writing we have to do. And you're like, well, it doesn't matter. It will matter. It will matter. Right? So similarly, for sine of alpha, we'd write S subscript alpha. Because if we don't start doing this, once we put a couple joints in here, we're going to have an alphabet soup and it won't fit on one page. So this is the simplification we're going to do. And so we get C theta minus S theta. Get it right here. S theta, C theta. Then our next one is R, Z, and what are we doing? Phi. Or Y of phi. So again, we're taking this and we're rotating it around the y-axis. And you can see that the y is not going to change. And since the rows are also unit length, we get that one for free. And then we just have to fill in our diagonals. So we've got our first one here. C phi S phi minus S phi C phi. And then our final one is R, not equal. RZ, I think I did psi. So for this one, 0, 0, 1, our last column. Since our rows are also unit length, we've got this, and then it's just C phi minus S psi S psi C psi. All right. So we've got, all right. So these are our basic rotation matrices. Using these basis rotations, we can generate any other rotation in the world. Right? Because we've got 3 degrees of freedom there, and there's only 3 degrees of freedom for this rotation matrix. And these rotations are orthogonal to each other. And so we can generate any rotation by composing these rotations together. That's why we call them basics. So let's talk about rotational transforms. And I thought this was kind of opaque the first few times I read it in the book. So I'm going to try to present it in a slightly different way, and maybe it'll work for you. The idea is I've got some rigid body S. In this case, it's my eraser box. And there's some point inside this rigid body, point P, that I'd like to be able to describe in my coordinate frames. And so I'm going to say this rigid body has bolted onto it some coordinate frame. Well, bam! It's bolted onto that. And then I've done some sort of rotation to S. And I want to know, well, what's happened to P? Where is P? How do I represent that? And so if I am given the coordinates of P in my frame that's bolted onto my robot, which is something that happens quite often, right? We know if we bolted on the coordinate frame onto a robot, we know where things are in relationship to that coordinate frame. But we want to know where it is in accordance to some base frame. And so when we are saying that we know what P1 is, that means we've got coordinates in this basis vector, which could be some, there's an animation, everybody say, ooh, you see that? Yeah, that didn't come for free. So we've got these coordinates, this U is my direction along my x1 basis vector, my V along my y1, and my W along my z1. So if I say I know where it is in a coordinate frame, that means I've got these three variables that tell me my x, y, and z in that coordinate frame I'm talking about. But what we like to do is be able to go into P0. And so what I have done here is I've just written out the first row in here because the other rows are pretty similar. So when I talk about P0, I'm saying in coordinate frame 0, what is P? And if I'm given P in coordinate frame 1, all I have to do is take P1 and then do its projection onto my basis vector. P1 dot and P1 dot Z0. I just have to project it and see, where is this point now when I project it onto my base frame, the unit frame. And so what I've done here is I've expanded each of those rows. And so remember what P in coordinate frame 1 is. Well, I just substitute that value. It's Ux1 times V Y1 plus W times Z1. And then I'm dot producting that with X0. Now the dot product commutes. So then I can commute that X0 into there. And now I've got each of my individual terms as a dot product. So what this thing is going to produce, actually a dot product, do I get a vector or a scalar out of it? Scalar. So I'm going to get a scalar across this top. And, but what we can do here, I'm going to take this third from the bottom here. I've got U x1 dot x0 plus vy1 dot x0 plus w z1 dot x0. But I also have ux1 dot y0 plus vy1 dot y0 plus w z1 dot y0. And I've got u x1 dot z0 plus u v y1 dot z0 plus w z1 dot z0. And so what I can do now is I can factor out my u, v, and w, pull those off to the side, and make a vector of those. And now I've got this transformation that is going to take my, that is going to tell me how do I transform from one rotation to another. So you can see that, this row here, my output is going to be a three scalars. But when I pull out my UVW, what I have now is three, I've got three columns now. And so this matrix that I have here in the middle is going to be a 3 by 3 matrix that tells me how do I rotate a point from one coordinate frame to another coordinate frame. And so what we have now is we're going to have different ways that we can talk about rotation frames. We can give them 3 different definitions when we're working with rotation frames. And so I've drawn here 3 little pictures to help you remember this. This is, I think, the first blank that's in your worksheet. So when I have a rotation matrix, and this is the term we introduced last week, we said that R is an SO3 or R is an SO2. What does the SO mean?
Special orthogonal.
So these are special orthogonal matrices. They're orthogonal in that every column multiplied by any other column is going to give you 0. Yeah, they're orthogonal. Means I project any column, I project this Z onto this Y, and I get nothing. There's no shadow when I project it, because they're mutually orthogonal. And so not only are the columns mutually orthogonal, but so are the rows mutually orthogonal. They're special. Why are they special? Yes. Yeah. So these 2 points, 2 things that make them special. I heard from Oman that it's because the determinant is 1. And the other thing that makes them special, yes, it's very easy to get the inverse of these. It's just the transpose. Do tell me your name again. Archie? Archana. Thank you, Archana. All right. And so the 3 new ways that we can talk about it is, we've got this point P. I have this point P on my stapler, and I want to represent it in 2 different coordinate frames. Oh, I moved this one. Should not have done that. Right? And so we can talk about how do we relate the coordinates of a point P in 2 different frames. And we can make this matrix R to do that. We can also talk about R is talking about how to change the orientation, a transformed coordinate frame. You give me this other coordinate frame, this R is going to tell me what's the transformation between those 2. And the third way we can think about it is this rotation frame is an operator. If you give a vector, I can apply this operator and rotate it to a new frame. So, and that's what we did in this last slide. We had this point P, so we're going to pop back to that slide to remember. So we have this point P, and we can talk about how this R is actually transforming it. We can think about rotating from a base frame into this new frame. And so let's do a rotation example here. So here I've got my box right like this, and I've labeled its far corner P. And I've got I've got the same base frame here, but I've taken my point and at PA, and then I rotated I did not move my base frame. I rotated it around. I want to know, well, where is PA after it's been rotated? When it becomes PB, what is PB? So we're just rotating this box about the z-axis by pi. And so the first thing we need to talk about is, what is this operator that we're doing? This R tells you what is this transformation from to be in 1 according to base frame 0. And we said it's a rotation of z about a rotation of pi about the z-axis. And so we know what this is because we have this value right here. So R is z by pi. What is the cosine of pi? We have -1, no sine, 0, 0, -1, 0, 0, 0, 1. So if we were to think about it, we could take 2 of these coordinate frames and we can see that's exactly what happens. So I've taken my coordinate frame here and I'm rotating it about z. And you can see that now x, oh wait, we did something wrong here. What did we do wrong here? what am I thinking about wrong then? So I rotate pi. That's what I did wrong. I only rotated pi. So I rotate pi around here. And now you can see the x is pointing in the opposite direction, y is pointing in the opposite direction, but z has not changed. And so this is our operator here. It tells us our rotation. And so now we want to know, well, what's going to happen to point PB? So I know what PB is in its initial orientation. And then I apply this rotation, and I want to see what happens. So P in the 0th frame is equal to this rotation times PB in its initial frame. Well, what is PB in its initial frame, in frame 1? We looked at PB hasn't changed its location in the box. Okay? And so PB in frame 1 is just going to be PA in frame 0. So this is equivalent to RZ pi times PA in frame 0. And so what is this RZ pi? Well, it's our rotation 1, 0, so we can write that as PB in 0 is equal to R 1, 0 times PA in 0. We've got our rotation applied here. Let's do another example here. So let's talk about this rotating a vector. So I've got a vector v. I want to know, v is this vector, but I want to apply a rotation. I want to rotate around y0 by pi over 2. So here's my show. So I've got my y0. I'm only going to rotate pi over 2. I'm going to rotate to this point here. And you can see that now my z is pointed in my x direction. So we'll give ourselves a little bit of room here. So what is ry pi over 2? Well, we've got our ry here. So we get a 0, 0, -1. So we're rotating downwards. Our y is not going to change. 0, 1, 0. And then our x direction, and you can think about it. You take your coordinate frame that you have drawn in your hand and rotate around y by pi over 2. So, and now our z-axis is going to be pointing in what used to be the positive y direction. And we know what v0 is. So I'm going to take this. I want to multiply it by v in 0. I multiply it by 0, 1, 1. And then I just apply my multiplication. So I want each of you to apply that multiplication, then we'll check ourselves. Multiply that out, check yourself. These basic definitions, right? We can be a coordinate frame representing, how do we relate the coordinates of a point P? I've got two different frames. I want to be able to talk about that in both frames. We can also talk about how we, it's a transformed coordinate frame, or we can think of this rotation matrix as an operator that takes everything and rotates it into a new frame. These are all equivalent definitions. And we will use all three of these examples in our class this semester. All right, I'm going to show you a picture. Does anybody recognize this picture?
Tea kettle.
This is a famous teapot, one of the first shapes that had Bezier curves that was coded into 3D representation. And anything, do you know anything special about the teapot?
Short and stout.
So it's an in-joke in computer science. This teapot has no bottom. And so, it's a joke in Toy Story 1. It shows up, I think it shows up in all of Pixar's movies. They show teapots somewhere in there. But it's got no bottom. Anyway, this is a teapot, and I want to apply a linear transformation onto it. So a linear transformation is something that can be represented by a matrix. So I'm going to multiply it by a matrix. And this one that I picked, the linear transformation I'm going to apply is A. So if you look at A is going to be a scaling transformation. And what a linear transformation is, I represent my object by a point cloud, maybe 1,000,000 points. And then I multiply A by each of these points. And it tells me where these points map to. In this case, A is just a scaling matrix, and you can tell because it's only the diagonal entries that are non-zero. And so what it's going to do is it's going to stretch out my shape in some way. The way that it's going to do this is it's going to make, in the x direction, it's going to get twice as long. So every x coordinate is going to be multiplied by 2. Every y coordinate will stay the same, but every z coordinate will be multiplied by 1/4. So it'll get squashed flat. So this is a linear transformation A that I'm going to apply to it. My only problem is that I have 2 different coordinate frames that I could be talking about. Maybe somebody's giving me all my points in coordinate frame 0, or maybe they've given it to me in coordinate frame 1. And the difference between these 2 coordinate frames, and they're actually both drawn on the same, in the upper right one, you can see that x is pointing downwards and y is pointing upwards. And you can see in blue, there is one that's pointed the opposite direction. And then what I've just done is said, well, that's how people in coordinate frame 0 look at the world. But if you're in coordinate frame 1, you're going to have x pointing down to the lower right. And so it's the same teapot. I've oriented the coordinate frames to be a standard presentation for people in coordinate frame 1 and coordinate frame 0. And so I want to say, if I apply A to the teapot in coordinate frame 0, how do I apply A to the teapot in coordinate frame 1? There was a question in the back. The fourth element there? The fourth element, that's a good question. So this is a hint towards the future. This is what's called a homogeneous transformation, in that it not only rotates it, but it can also translate the object. And so we are going to be using 4x4 matrices by the end of the lecture. And so what's happening is the top 3x3 matrix is a rotation matrix. The last column is a translation column. The translation ones in this case are all 0, so all it's doing is a pure rotation. But excellent question. That's what's going on here. We're going to hit this a lot later. All right. So these similarity transforms, they're all going to stretch that teapot so that the spout is longer and farther away. But if we want to do that in coordinate frame 1, we can't just directly apply A to coordinate frame 1. Because if we apply A to coordinate frame 1, it would be extending it along coordinate frame 1's x-axis. We don't want to do that. We want to be, in coordinate frame 1, we want to be expanding it along the negative y-axis. And so how we do this is what's called a similarity transform. And those of you who have taken Laplace, how many of you took signals and systems? All right. So it's the same trick that we do in signals and systems. I've got this beautiful transformation that I want to apply in coordinate frame 1, but I'm not in coordinate frame 1. I'm in coordinate frame 0. So what do? First, put it in coordinate frame 0, apply the transformation, and then put it back into coordinate frame 1. And so if you've taken Laplace, this should make a lot of sense to you. Laplace or Fourier. The idea is, we're in a different domain. We just transform it into the domain where we've got the operator, apply the operator, and then push it back in the other domain. And so, since the operator here, in this case, is A, that's what we want to apply, and we've got this R, what we need to do is first, take it out of that coordinate frame and move back. So this is what we're doing. It's called a similarity transform. Because you've got this coordinate frame that's defined by these basis vectors. And so I'm just saying that A is a linear transformation. And we want to have B be the same linear transformation, but in a different coordinate frame. Then we want to relate these two together. And so what we're going to do is we want to know what is B equal to. Is this hidden? Would it be better if I wrote over here? So I'm going to say B is equal to, well, I want it to be equal to A, but obviously I can't do that. So what I need to do first is I need to do the inverse of whatever transformation relates coordinate frame 1 and 0. And then I need to apply that rotation at the end. So first I'm going to invert that, and so the transformation between those two is going to be R1, 0, R1, 0. Take the inverse of that, apply the transformation, and then translate it back into my coordinate frame. It's just like the plus. So we're first switching into the coordinate frame where A would apply, applying A, and then switching back so that we're in B. I want you to remember this because this is something that we're going to be doing when we put, we've got a robot arm, and if I bolt onto the end of the robot arm a tool, there's some sort of transformation from the end of the tool, from the gripper to the end of the tool. I have to be applying the similarity transform. So so if I know the transformation from one to the other, I've got to find that full transformation. I've got to apply the pre and post multiply. Right. A skill that I want you to have is to be able to take a rotation transform and then be able to draw it. So this is a rotation transform. I want you to be able to draw that on your piece of paper. So to start by drawing on here, I've got my x0, my y0, and my z0. And then I want you to draw what happens when I apply this. What is this rotation matrix here? So if you have all sorts of colors, kudos for you. Remember, what R1 and 0 is giving you is what is x1 and 0, what is y1 and 0, and what is z1 and 0. So x1 in frame 0 is going to be nothing in x and y, but it'll be -1 in z. So that means that this one here is x0. Right? When we look at y0, which direction is y0 pointing? Which direction is y1 pointing? You say it in the back. Yeah. So we've got y1, and then our z1 is going to be pointed along this. And since we have our right-handed coordinate frame, we didn't even have to have that. We know that. Take your hand and rotate it. The only way that this would work is if z is pointing along the x0. Right. So if A is this rotation r z theta relative to my base coordinate frame, then the same A relative to frame 1 is going to be given by this B. So this is a similarity transformation. So B is equal to, well, it's not equal to A. We've got to take A and we've got to first undo the rotation that we're applying. This R1, 0, -1, and then we've got to reapply it afterwards. And so, really quickly, I want you to write in your paper, what is the inverse of that matrix? Like, oh, right, matrix inversion. Yes, write the transports. Really quickly, on there, I'm going to switch colors. These are why we love special orthogonal matrices. Because we can write that as B is equal to here. All right. So we can just apply this inverse with no trouble at all. 0, 0, 1, 1, negative 1. And then we said that our A is going to be a rotation of theta about the z-axis. Well, we've got that right over here. So it'll be c theta minus s theta, c theta, 0, 0, 1, 0, 0. And then we've got our unrotated matrix, 0, 0, 1, 0, 1, 0, and 1, 0, 0. And now you'll be doing a lot of 3 by 3 multiplications. So race me. See if you can get it before I do. Or see if you can make less mistakes than I do. And actually, I should just have you do it. There's more, you'll get more out of this if you do it. You do the multiplication. Yes, ma'am.
Sign of the first matrix.
Say that again.
After you take the transpose of the first matrix, the sign has to be changed.
Oh, yes. That's terrible. Absolutely right. It's going to be Rx of negative theta. And so this is a similarity transform. And we can concatenate these together. Now we have, since we're now in this other coordinate frame, now we can just multiply by b and we can tell where every point on our robot is just by multiplying this b. And this will apply to our homogeneous transformations that we will do by the end of the class. So we can do this and not only do rotations, but we'll have to use the same math to do translations. So we'll know where every point on the robot is in 3 space. So now we go to my favorite part of this lecture. And this is the idea of composing rotations. Because we are looking at serial length manipulators. So there'll be a rotation by the body axis, by the shoulder axis, the elbow axis, the wrist axis, and around the fingers. So we want to know, what is this total transformation? How do I compose all these rotations together? And so I start with a big if. If I've got these 2 coordinate frames, and they are related, my first blank here, if they're related by rotation matrix R, are 1 and 0. So my first frame here is R 1 and 0, and my second frame there is going to be R. Oh, we don't need to do all. No, it shows them all at once, so that's terrible. And my next one is going to be R 2 and 0. This rotation matrix tells me how do I jump between these 2. Well, if I've got P0, well, that's just equal to P. Remember, P is this point that actually exists. P0 is, what is its coordinates in frame 0? P1 is its coordinates in frame 1. Well, these things are related by R1, 0. Similarly, P1 is equal to a transformation times Pn2 by R2 to 0. Tells me, how do I take this point that's in coordinate frame 2 and get it in 2 and 1? I want to get it into frame 1. I apply my rotation matrix. Question in the back?
Should that be, so the second line, should it be all 0 or all 1, x1, y1, z1, and all 2, x2, y2, z2? They are related.
Say that again.
So the second line should be all 1, x1, y1, z1, and all 2, x2, y2, z2.
No. If I want to know from 0 to 2, then that's going to be, what is 2 in frame 0? If I was talking about 01, frame 1 and 2, then I would say I need a rotation that goes from 1 to 2.
Well, isn't that what you're trying to prove eventually? So those 2.
Well, what I'm finding here is I have let's say that I've been given R01 and R02. The relationship between these one is some unknown matrix R2 and 1. I've got to figure out what is this rotation matrix. So let's get there. Okay, well we know that P0 is going to be equal to R, and the relationship between P0 and P2 would be this P. I'm trying to figure out what is my frame 2 in coordinate frame 0. I think you're right. I agree. This slide would be a lot cooler if I changed that second line to be ones. I'll do that. So let's say that I was actually just given, my step transformations between these two. So I know what R10 and R21 are. What I don't know is what R20 is. What is this total transformation from frame 0 to 2? Well, what I can do then is I know that this total transformation is a composition of rotations. This is that P0 is equal to R10 times R12 times P2. And so that means that this R02, R2 in frame 0, is equal to R1 in frame 0 dotted with R2 in frame 1. And so this is our rule of our composition of rotations here. And it shows up in this beautiful transitions here. Now, one thing I want you to watch is that our cancellations then can go from a slash from the bottom left to the top right. So we're canceling out these and we get our total rotation of R2 to 0. So, yes, in fact.
So we have 3 different reference frames in this particular scenario. Right?
Yes.
We've got 0, 1,
We should draw that out. We've got coordinate frame, our base frame. We've got coordinate frame 1, and we've got coordinate frame, coordinate frame 2.
Will this work if we have 5 coordinate frames?
Yes. That's my next slide.
Oh.
Yes, it is. That's why it's my favorite. These compose, the order matters. The order that you apply these matters. But we can compose this to any number of links. And so how we refer to that in robotics is we'll talk about an n-link manipulator, where n can be any scalar number, any integer number. And then we just multiply these successively, one after the other, to get our final value. And so there's some rules when we compose these rotations, because we have to know which frame are we talking about. So the frame relative to which the rotation occurs is the current frame. So if I'm in frame 1 and I want to, my frame 2, I'm in frame 1, that's my current frame, and then I rotate into frame 2. Whereas my base frame is this fixed frame. It's bolted onto this floor. I can't change it. So I can either talk about my current frame as I'm moving my way outwards, or I can talk about my base frame, my fixed frame. And so if your rotation is performed with respect to the fixed world coordinate frame, what we're going to do is pre-multiply that multiplication when we're composing these together. But if the rotation is performed with respect to the current coordinate frame, then we post-multiply to compose these together. So in beautiful blue text, when it's a fixed coordinate frame, we pre-multiply by that rotation r. If we're talking about, we're at this frame and then we rotate from that frame to the next, with respect to the current frame, then we post-multiply. So let's do an example here that'll hopefully make this very clear. So just to remind, when a rotation is formed with respect to the fixed world frame, what do? Pre-multiply. When it's with the when it's with the current frame, we post multiply. So here we've got an example. I'm going to do the first two stages, and then I want you to do it. So again, I'm going to erase. I'm going to favor this side of the room now. The first thing we have, we want to know what is R equal to. R is equal to a bunch of rotations. And if I look here, I can see some of them are according to the world, the fixed frame, some are according to the current frame. But we're going to go in, since I don't know how many, well, I can count how many there are, but I'm just going to start in the middle of my box here. So the first thing that I do is I want to rotate by alpha about the world x-axis. So x, alpha, there's nothing to pre or post multiply, this is my first stage. Next one that I have is I want to rotate by beta about the current y-axis. So I've rotated around x, now I want to rotate around that axis an additional beta. So I'm going to post multiply y by beta. All right, we'll do one more and then it'll be your turn to finish up. Next one is I want to rotate about 5 about the world x-axis. So this is the world axis, so I'm going to pre-multiply x 5. All right, there's two more on there. I want you guys to write it down. Write this down on your sheet of paper. Those of you who did not come with a piece of paper, let me know and I will bring you some paper next time. X about alpha, and then we rotate around the current, so that's a post multiply, and then we, by the fixed, we pre-multiply, and then we do it about the world. So we're going to pre-multiply alpha, pre-post, post, and then our pre for the last one. Now, I'm not going to accept this for the exam. I'm going to say, thanks for trying. And why won't I accept this? How can you simplify this?
Oh, with summing of, for example.
Yes, I want you to look for if there's any two rotations that are on the same axis. You're looking at it, objectively, you can't tell the difference. Those things sum together. That simplification is too easy to do. And so you can see that I got z and then I got two x's that are right after each other. So we can simplify that. That's a total rotation around the x-axis by
Alpha
5
plus
alpha. And that's what I want to see on your exams. Right? Because life is too short to be writing all these letters down. But sometimes there'll be a very nice simplification. This composition of rotations, if you're rotating around the same axis, then we can just add those rotations together. And that has significance. Later, I think, next class we'll talk about something called gimbal lock. If you don't know what gimbal lock is, Wikipedia's got a nice page on it. The idea of if you have any successive rotations that are on the same axis, then it turns out you lose a degree of freedom because their rotations both are going in the same direction. Okay. So now, let's go beyond rotation matrices. Let's go into this homogeneous transformation, where we're talking about not only a rotation, but also a translation. And so we're going to represent this. We did rotation matrices with a big R. When you see a big H, you're going to know that's a homogeneous. Everybody say homogeneous.
Homogeneous.
Yeah, up until a couple days ago, this slide said homogeneous. That was just wrong. Right? Homogeneous. That's what we want. All right. And so this homogeneous matrix that we have is going to be composed of two things. We've got H is equal to, we can divide this thing into 4 quadrants. And this first one is going to be a 3x3 rotation matrix. If you want, I can say this is a 3x3. And then if we got a D, this is 3x1. And then we've got a 0, 1 by 3 zeros. There's 3 zeros in it. And then we've got a 1 here that is 1x1 matrix. This is how we're building these homogeneous transformations. So we've got R, D, 0, 1. And so this R is, and what does SO3 stand for?
Special resort.
Yes, so this R, and this means that this is in the set of special orthogonal matrices of size 3. And then my D is going to be this in notation, and the blackboard bold says that D is going to be in space of real numbers, 3-dimensional space. So this is Euclidean 3 space. So this D tells me what is the translation of my origin, and this R tells me how did my coordinate vectors rotate. We put those two numbers together. Remember, this is only 6, and like there's some bloat going on here. Remember, there's 6 degrees of freedom for an object in free space. How many numbers do I have here? 16, right? Like, whoa, what's going on here? Well, 4 of these they're always going to be the same. 0, 0, 0, and 1. This 3x3 has a bunch of constraints on it. It's got 6 constraints. So I do only have 6 degrees of freedom, and I've got this 4x4 matrix. And like, whoa, that's not efficient at all, Dr. Becker. And the efficiency of these homogeneous transformations is that we can apply them successively. We can compose them together. And so figuring out how you compose one joint after another is just going to be multiplying these matrices together. And that is the beauty. That's why we're going to do this. And so what we want to do is, if we want to work with vectors, so we can think of our robot as a point cloud of 1,000,000 points. And when we apply some homogeneous transformation, we want to say, well, where is that point cloud moved to? The constraints that we're applying to this means that our robot will not expand in any direction. We're not stretching it. All we're doing is rotating it and translating it. That's what makes it a homogeneous transformation. It's not going to gain any more volume. The point cloud will still have the same volume. It'll just be moved to a new location. And so we have to augment these vectors. And so how we're going to do that is we're also going to use a capital letter. So if I have my P, the coordinate frame 0 is equal to U, V, W, what I'm going to do is augment this in cap P0 is equal to U, V, W, and a 1 there. So if my homogeneous transformations are going to be 4x4s, so in order to move my point clouds, I've got to augment them to be a 4x1 vector. And so we get this U, V, W, 1, and the same thing. So this homogeneous transformation, we call it a rigid motion, because we're not bending the robot, we're not stretching the robot, we're not inflating the robot, right? The robot, this is a rigid body, so it takes the same volume, it's the same shape, it's just new orientation, new position. So if the rigid motion H is relative to the current frame, what do you think we're going to do? We're going to multiply it. The current is going to be post-multiply, quite right. And if it's relative to the fixed frame, then we're going to pre-multiply. What that means is now I can concatenate a bunch of these homogeneous transformations together. And this, this works, right? If I'm talking about, I'm going to be a robot right now. And so I do a homogeneous transformation by a rotation around the waist, and then I do a homogeneous transformation rotate about the shoulders. That can be pre or post-multiply. Rotation around my shoulder joint.
Post.
That's a post because I'm talking about my current frame. If I then rotate it around my elbow, that's going to be a
Post.
post. And a post for my wrist and post for my fingers. However, if I put that thing on a trailer and move it somewhere else, what should I do?
Pre.
I'm doing that with respect to its current frame. If my robot grabs onto somebody huge and immobile that's heavier than my robot and lifts my robot up in the air, what would I be doing to talk about that homogeneous transformation?
Pre.
I'm free, because he is, according to my fixed coordinate frame. And that can happen, right? You take your robot, if it's strong enough, it can lift its whole body off the ground, right? And so that's my pre-multiply. All right. So there are my lessons. What I want you to do for the next class is to start looking through 2.5 and 2.6. And we are taking these rotation matrices a little bit slow. And that's because it's foundational for the rest of the class. So you can read ahead if you're bored by these. But we've got to have a good handle of these rotation matrices. And again, I will try. Well, people are not here and still cannot come to class. I'm not going to give you a quiz. But we will use some announced quizzes to help you practice and make sure you're ready for the exams. Okay, now we've got some time because we ended early, so I want you to do this in-class worksheet now with some people who